Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my second video on practical math. Today, I'm going to talk about how one can estimate pi by performing a random process, an experiment involving a random process. And I'm going to give you two examples. So let's begin. So the first example I want to talk about, I believe this is the first um, random experiment that was ever devised to try to estimate the value of pi. There was a French mathematician named Buffon, I guess Georges Louis Crack, also known as Comte de Buffon. He was pretty famous. He was a famous mathematician and scientist and surveyor, and he did a lot of pretty important stuff, I guess, in the 18th century in France. But one thing he was known for was this Buffon needle problem. And the problem's pretty simple. So here's how it goes. You're supposed to imagine that you have a floor consisting of wooden panels, each with thickness T, and then you have a bunch of needles. Say you have capital N needles. Each needle, they're all the same length. They all have length L, where L is less than or equal to T, so that a needle can't cross two panels, but it can cross one. So then the question is, if you just drop these needles on the floor at random, what fraction of the needles do you expect to cross a boundary between two panels? And it turns out you can actually compute this just using a very simple model of uniform random distribution. So you're supposed to assume that the distribution of both the angle, the orientation of each needle, as well as the distribution of where the needle falls, the center of the needle. Uh, if you assume that both of those distributions are uniformly random, then you can calculate this the fraction, and it turns out to be um, 2 over pi times t over L, or L over t. And in the special case in which L equals t, in which the length of the needles is the same as the width of each panel, then this ratio just becomes 2 over pi. And what that means is that in order to estimate the value of pi, all you have to do is drop a whole bunch of needles on the floor, some large number, capital N of needles. And if you do that, you'll find that the you can estimate pi as equaling you just invert the formula, you get pi equals two 2 times capital N over little n. Um, and if you calculate that ratio in the limit in which capital N goes to infinity, and the limit in which you have a very, very large number of needles, you can get an arbitrarily precise estimate of pi. Pretty neat. And the picture I showed on the bottom, I mean, obviously, you probably wouldn't want to do this in real life because you have to buy a lot of needles. You'd also have to make sure that you have the right kind of floor. But you don't actually have to perform the physical experiment. I actually made a video on this a few weeks ago. There's a very commonly used technique in computer program called Monte Carlo simulation. So instead of actually, buying the needles and making sure you have the right kind of floor, all you really have to do is write a computer program, which is pretty easy to simulate this experiment. And this was actually done. I didn't do this myself, but somebody did this. I picked this picture off the web. Somebody actually did this simulation on the computer, and I think you can find stuff on the web that'll simulate the fine needle problem. So they did this, and if you look at this picture, I don't actually know how many needles they simulated here. Looks like around 100 or so. And I assume the length of the needles is equal to the width of the panels. And the needles shown in red are the ones that cross a tile boundary, and the ones in green don't. And I didn't actually count the number of needles across the boundary. I didn't estimate pi this way, but you can do it yourself. I mean, you can count the needles, I think, pretty easily, and determine a percentage and see how close it is to 2 over pi. Or alternatively, you could try to estimate pi using the formula I gave you, 2 times capital N over little n. Um, and That's just one way you can simulate pi. Actually, there's a much simpler one. You could just, I mean, this is probably the simplest one you can do, at least the simplest that I know. So, computers are very good at generating random numbers, in particular random real numbers with a uniform distribution. So you want to generate a random number from 0 to 1, such that the density is uniform in the limit in which you generate a large number of them. Well, that's easy to do. And if you do that, here's another way to estimate pi. Take 2n, again, capital N is some large number. So take 2 times capital N, random numbers from 0 to 1, just generate them on your computer. And it has to be, the reason I call it 2n is because it has to be an even number. And the reason it has to be even is because we're going to pair up these random numbers. What we're going to do is we're gonna write pairs, ordered pairs. So we're going to call them x sub k comma y sub k. So if you like, our random numbers we're generating are just x1, y1, x2, y2, so on, all the way up to xn, yn. And the reason we're doing that is because the next thing we do is we calculate the sum of the squares of xk and yk. We calculate xk squared plus yk squared. And it turns out that the fraction you expect of those ordered pairs to have a sum of squares less than 1 is pi over 4. That's very easy to prove. I mean, since there's a uniform distribution of the x's and y's, what you're really getting here, I didn't show a picture, but what you're really getting here is you're getting a bunch of points in the xy plane. You're getting points where x and y vary uniformly from 0 to 1. That's just a unit square in the xy plane. And the points where the sum of the squares of x and y is less than 1 are just the points within the unit quarter circle. So the quarter circle just has the equation x squared plus y squared equals 1. And all the points whose the sum of the squares of xk squared plus yk squared less than 1 is just going to lie within that unit quarter circle. And it's very easy to compute the area of that quarter circle. It's just pi over 4. So the ratio, the fraction you expect of these points for which this inequality holds is just pi over 4. So to estimate pi, you just take 4 times the number of points that lie within the unit circle and divide by the total number of points you started with. That gives you an estimate of pi. And I actually did this. I actually wrote some computer code to run this experiment. Pretty simple computer code. I wrote this in about 15 minutes. Very simple to write. I already told you the algorithm. I just wrote this in C, which was very easy, and then I ran the simulation. And I don't know if you guys can see this. The print's kind of small here, but I actually simulated this for values of n ranging from 1,000 to 1,000,000,000. Even 1,000,000,000 didn't take that long. Computers are very fast these days. So running 1,000,000,000 simulations took about a minute. And I don't know if you can see the results I got, but they get closer and closer to true value of pi. The estimate I got for pi with 1,000,000,000 points is 3.14149. It only differs from pi in the fourth decimal place. So it's within 1 part in 10,000. And they get closer and closer to pi. I mean, even the case n equals 1,000 isn't too bad. I got 3.128. Not a great estimate, but it's within about 1%. So, you don't have to use a huge number of points. But like I said, since computers are very fast these days, it's very easy to do 1,000,000,000 points, which is what I did here. And I got an estimate of pi that's correct to about 4 decimal places. So not too bad. So anyway, that's how you can use random processes to estimate the value of pi. And that concludes my video for today. Thank you for watching. Long live math, and I'll see you guys next time.